My name is Suresh Srinivas. I've been working at Yahoo in Hadoop HDFS team for the last 3 years. I'll be transitioning over to Hortonworks, and my co-author is Sanjay. You heard his talk today in the morning. So today I'm going to talk about some of the Release 23 features, mainly HDFS Federation, which is one of the major features that we are introducing in Release 23. And then I'll also discuss about other new features that are coming. So the agenda is going to be, first we'll look at HDFS architecture and see the current limitation that it has and how HDFS Federation will address some of these limitations. And then I'll also talk about some of the other key features that are going into HDFS that is of interest to everybody. And we'll also look at some of the future things that we'll be focusing on for HDFS. So in HDFS, there are two main layers. The first main layer is the namespace. Namespace consists of directories, files, and the blocks that make up a file. The namespace supports all the namespace-related operations, such as creation of file, deletion of a file, listing files, modifying files, things like that. The second layer, which is the storage layer, or the block storage layer, has two subparts. One is block management, and block management is the functionality that defines the cluster. So that is where all the data nodes register. The entire storage of the cluster is discovered and managed. The block management layer supports block-related operations, such as adding a block, deleting a block, listing blocks, things like that. Block management is also responsible for ensuring the replication of a block. So it ensures that if replica count is below the replication factor of the file, it creates another new replica. It also removes over-replicated blocks by deleting extra replicas, right? So the bottommost layer is the data nodes, which are used for storage, right? So the namespace and the blocks together, that can be called as a namespace volume, and it is implemented using name nodes and data nodes. So today, a name node supports both the namespace and the block management. They are both collocated in the name node. And their data nodes are used for storing the block replicas. And the block files are stored on the local file system. Okay. So now let's look at, with this background, let's look at some of the limitations that are there in the architecture. The first limitation is there is a single name node. So the entire file system of many thousand data nodes has a single name node. And though you can scale the cluster storage by adding more data nodes into the cluster, the namespace cannot scale beyond a single name node. So whatever a single name node supports, that's the size of the namespace you have. So this results in limitation on number of files and blocks. They are the mainly they are the objects that take up the name node memory. And the fact that name node also stores the entire namespace in the memory limits how much objects can be there in the namespace. So currently in Yahoo, in some of our biggest clusters, which are 4,000 data node clusters, we have hit a limit of 250 million files and blocks, addressing up to 12 to 16 petabytes of storage for the kind of average block size we have. The other problem with a single name node is the performance, right? So all the namespace operations are handled by a single name node, and you cannot scale beyond what the throughput a single name node supports. This is going to be a problem with next generation MapReduce, where current MapReduce has certain limitation in number of tasks, concurrent tasks it supports. As we move towards MapReduce next generation, the HDFS single name node would become the bottleneck for even MapReduce framework. The other problem that typically happens in HDFS or Hadoop is typically used as a multi-tenant shared system, so that you don't have your own dedicated clusters, where multiple users and applications are using the same cluster, and you cannot have a separate namespace for different tenants. Maybe finance wants to have a separate name node from other applications. That is not possible. We have also seen that this lack of adding separate namespaces results in some of our clusters an experimental application sort of overloading the name node and affecting the SLAs for our production clusters. You could also look at applications which are different categories. For example, you might want to have an HBase, a name node for or a namespace for HBase, which is separate from other other applications that's on the cluster. The other limitation is tight coupling. Today, namespace and block management are very tightly coupled. They're actually two distinct services. This tight coupling is a result of both namespace and the block management being on the same name node. So this has resulted in no clear separation or no clean separation between these two different functionalities. Now, one could look at if these were separate, the way you would scale the block management, right, and scale the block storage layer to have more blocks, you could scale it differently compared to a file system namespace. It's easier to horizontally scale it. It also today, because Namenode has both namespace and the block management, if you were to have just namespace separated out, you could also look at the namespace implementation becomes a lot simpler, and scaling it is also simpler because you don't have to worry about the block management aspect. The other key thing that I want to bring up is, if you look at this layering, block storage could be a generic service where applications that don't want to use a file system for storing, they could directly use a block storage, right? So currently, namespace is one of the applications that is using the block storage. You could see HBase directly sitting on top of block storage without having to depend on Namenode. Or you could also look at building foreign namespaces which have different characteristics compared to HDFS Namenode, and try it out on the same storage layer. Right? So now the other key point that I want to bring up is some of this isolation that I was talking about is not just a problem for large clusters, right? So it's a problem for even small clusters where you may want to separate out your applications to different namespaces. Right. So let's cover HDFS Federation and look at some of the limitations that we are addressing. With HDFS Federation, we support now multiple independent namespaces. So what I mean by independent name nodes or namespaces is one namespace or one name node doesn't have to coordinate with another name node for providing the file system functionality. And in this picture, a namespace volume is a namespace and a corresponding block pool that the namespace uses. This also uses the same set of data nodes for storage for all the namespaces that is in the cluster. So data nodes provide to the namespaces block pool, an abstraction called block pool for storage, and data nodes are not partitioned for different namespaces. They are used by all the namespaces in the cluster. So this improves resource utilization in terms of disk I/O and storage, things like that. Let's look at some of the key ideas and benefits and how this enables some of this separation enables scaling, and as well as opens up the framework where we can do some more innovation. The first key point is the cluster-wide namespace is distributed among multiple namespaces, which are all stored in name nodes. The key thing is this design is a lot simpler because we are not making any name node changes. So today, name node is very robust, and we did not make a lot of change in the name node where two name nodes have to coordinate and locking across two name nodes, things like that. We avoided that. So a master or a name node supports only one namespace. So there are no multi-masters for a single namespace volume. The other thing that is also key here is the abstraction of block pools. So since block pools are independent in the storage layer, that enables the independence at the namespace, where you don't have to you don't have to coordinate for block IDs and how you generate block IDs, things like that. The other key thing is one could envision, with the block pool abstraction, you could, have some innovation around it where you could have block storage layer on top of it. You could build different file systems or, directly applications that use block storage. Not only that, you could have different categories of block pools. For example, one could have a block pool for MapReduce shuffle output, which has different characteristics, where at the end of the job, you can garbage collect it. You could also look at a block pool that makes distributed cache more efficient, where it caches the data and doles it out instead of having to hit the disk. So some of these new experiments can be done with different categories of block pools. In future, what we are thinking of is to move block management out of Namenode into a separate layer, and that simplifies the HDFS Namenode. Right? It also enables other applications for directly using block storage. And one could, in the future, have a truly distributed Namenode on top of this kind of a block storage without having to worry about block management. Right? Let me go over some of the details of where we are at with the federation. Now, as I said in my earlier slides, it's a simple design. Very little change is done to the Namenode. Most of the change is done in the data node configurations and tools. Now, even in data nodes, what we ended up doing is the hierarchy, which was flat with just set of blocks. Now we have added block pool in the hierarchy, where blocks are stored under block pools, and these block pools belong to a namespace. So that's the main change. The core development took roughly 4 months, and one thing that, the reason why I say first phase is we have not separated block management out of Namenode. They continue to live in the Namenode. This is done to keep the changes that we are making, small and get the release out faster. This could be done in the future. We have also, I want to emphasize one thing, which is, I don't want to use federation, and so what do I do? Do I need to, how do I migrate to this new release? One of the key requirements when we were developing this was to ensure that the existing deployments that use single Namenode are not forced to make changes in their configuration. So the existing deployments work as it is with the same configuration they are running today. We have also added a few other capabilities with the federation. One is, now you have multiple name nodes. So today, Namenode has a web UI. We have built equivalent web UI for the cluster level management. And in this web UI, you see cluster level summary of how much storage is available, how storage is being used, things like that, similar to what Namenode today provides. We also have a list of name nodes that are in the cluster, and then you can click on the name node and go to Namenode web UI. So this web UI is useful for managing multiple name nodes within the cluster. We have also added decommissioning status at the cluster-wide decommissioning status, which you can monitor from this web page. We also modified the existing tools to work with, now that the HDFS cluster has multiple namespaces, decommissioning, balancer, and some of the other tools now work with multiple namespaces. So decommissioning, works in conjunction with multiple name nodes or namespaces, and balancer also does the same thing and balances the storage utilization across the cluster. We also have added 2 different kinds of balancing. Today, the balancer balances storage across data nodes. The new balancer balances storage across data nodes as it is done today. It also has an option where you could also balance the storage within a block pool. Right? So now, in federation, now you have multiple namespaces. So in today's cluster, typically, the configuration has a default namespace or a default name node, and all the applications are working with that default name node. Now, how do applications have to change where to deal with multiple namespaces that's available, and how do they deal with it? So the key idea here is you identify the data using a name, right? And the key idea is to share the name that is used to access the data and share the data that way. One way to do that is a globally distributed single namespace. In here, what we have done is a much simpler approach where we have introduced, and this is available on the trunk, we have introduced client-side mount tables, which is a special file system. And you can use this file system. And what you do is you mount the different namespaces. In this case, you see 4 namespaces, and they are mounted on using client-side mount tables to give a unified single view of the cluster namespaces into a single namespace. So an administrator for a cluster which has multiple namespaces could define a client-side mount table, thus providing a single unified the namespace view that is shared across all the applications and users. This also adds the flexibility where an application could choose to have its own way of looking at the data and then define its own client-side mount tables and map it to how it is stored on the cluster. And applications have the flexibility to do their own client-side mount tables as well. So this enables that flexibility. Now, the other thing that I want to highlight here is the definition of the mount points for the client-side mount tables is not available through a server. So that avoids single point of failure, where if you don't have that server available, you no longer can go through your the directories that are mounted, and you won't be able to access the underlying namespaces. In here, it's done through configuration. It's all done on the client side. It also avoids any hotspots on the servers that are doling out the real namespaces that are mounted on root or top-level directories. Now, so that sort of concludes some of the federation-related information that I wanted to cover. There are other things that are also happening in release 23. There are some key improvements that are happening. Now, you might have heard in different blogs and stuff like that, where HDFS IO is not favorably compared with somebody else's solution. I'm sure Srinivas, who is going to talk next, probably will talk about this. So now most of these benchmarks are on our 20 release. We have made a lot of a lot of improvement from our 20 I/O throughputs, and there's a lot of activity that's happening in the community. The first one is the append implementation that we had in 20 had initially some problems, and it also has some problems at a higher scale, where we had some block-related corruptions and things like that. This has been implemented afresh on release 21, and this is being tested now under scale at Yahoo. So the new append implemented flush, sync, and I think HBase would greatly benefit out of this more stable version of these features. We have also been optimizing the I/O for HBase usage. There's a lot of good work that is done by Todd, Nathan, Kival on the HDFS JIRAs. So some of these improvements are, we used to have a client, if client had to open a connection every time it was doing a short read or a random read. So there is a change that has gone into the trunk where the connections are reused from the client. And with this, some of the benchmarks that is published on the JIRA shows 35 to 65% improvement in random reads. It also shows approximately 40% improvement in the latency as seen by HBase in HBase testing. We also made a change where, when clients read the data from the HDFS, there's a CRC validation that happens, and this is a compute-intensive part of the read, and there's a lot of improvement that has gone in here. We replaced the previous implementation of CRC with pure Java-based CRC implementation. By the way, I have Jira's here for people who are interested. You can go, look at some of the details there. And this pure CRC implementation, Java-based CRC implementation, improved the CRC by a factor of 2x. There is also an ongoing work related to further optimizing CRC. This is HDFS 2080, and this is not committed yet. This shows 2.5x improvement and also reduces CPU on the client side by a whole lot. There is also a change that is done where this is a change that has not gone in, but there's a change where we are improving the locking structure on the data node, and this helps in case of multi-threaded readers. We have seen an improvement of 15%, and this is primarily targeted towards HBase, right? And also for the readers on the data node side, there is an improvement in terms of threading model where pool of threads are used. This has shown 10 to 15% improvements in reads. So just to reiterate, there's a lot of work that is going on to to close the gap, and this is going to be available in release 23. And I think this improvement is continuous, and community is participating in this, and there are a lot of HBase guys are also influencing these improvements. Right, there are other set of features that's available in 23. Some of them, some operational features are we changed some of the we optimized some of the startup related time for HDFS. This is for a 4,000 node cluster that I'm talking about. The time now went down from 1 hour to 20 minutes. Upgrades used to take a lot more time, and this has been optimized where we go from 3 hours to 25 minutes. So these times should be much smaller in case of smaller clusters. The other important work that's gone into trunk, which is also available in, by the way, it's been backported to 0.20.204, is disk fail in place. With high-density data nodes becoming available, we are going from data nodes which are 4 terabytes to 24 to 36 terabytes. Now, in such a cluster, a loss of data node takes away a huge portion of the available storage to the cluster. So we have made changes here where data node continues to run with failed disk. We also have some best practices where you can, if you reboot the data node, it comes back up. I'm running slow, in covering some of these things, so I'll go much faster. We also have some improvements in storage efficiency in terms of HDFS RAID that's available as a contrib module. We've also modified some of our FS image and edits the way it is stored, and this is much cleaner, should help us in high availability. We have also done some write pipeline recovery changes where, if in a pipeline, if a data node goes down, we recruit a new data node into the pipeline, which should improve the robustness. This should also improve decommissioning. We have also cleaned up data node protocol. This is towards more, wire compatibility. We have moved this to protocol buffers. We have also made some matrix changes, and we made a change in a name node to use read-write lock that has improved the name node performance by a factor. Now, some of the future changes that are that is beyond release 23. Some of the things that at a high level we are looking at are high availability for name node, which is everybody's favorite topic. This work is in progress. There's an umbrella Jira that's created, HDFS 1623, and there is a lot of activity that's happening in that. Wire compatibility, which we have started working on. Their data transfer protocols have already changed to use protocol buffers. We are also doing the same thing for RPCs. The I/O performance improvement is something that's ongoing, and I think I see community rallying behind Hadoop here and making a lot of changes and improvements here. We are also considering, and these are now I'm coming to things that we are sort of thinking about, where we could have partial namespace in memory instead of storing entire namespace on name node in memory to further scale. And then we are also constantly making more management and operability improvements. Now, these are some of the key features that have gone in. There's a lot of work that goes into HDFS and Hadoop in general, and you're welcome to contribute as well. Okay. So that concludes my talk, and thank you for attending. And if there are any questions.
Two questions. The first one is, when you have these federations, does that mean each data node have to talk to multiple name nodes so that you have to do multiple heartbeats? Correct.
So I did not cover this in this slide because of lack of time. So the way it works is data nodes, because we don't have a separate block management layer, right? Block management still lives in the name node. And so the data nodes register with all the name nodes that are there in the cluster, right? So they register with it, they send periodic heartbeats, and they send, data nodes send block reports for the block pool that a particular name node owns, right? So that's what happens. And these are done in separate threads for each of the name nodes, so that one name node cannot block, interaction of data node with the other name nodes.
I see. My second question is, can you elaborate or explain the difference between this level of federation versus the federation of multiple DFS clusters?
OK, so in here, the key difference is one could run multiple data nodes, right, and each data node registering with different name nodes. The problem there is you cannot optimize all the disk I/O, right? In this case, there's a single data node that's managing all the disk I/O and doling out blocks and stuff like that for all the namespaces. And also, all the namespaces are sharing the same data node, right? So your storage utilization, for example, you could have multiple clusters where one cluster is completely overloaded, and it's running out of storage, and there's another cluster that has a lot of free space, and you cannot use it, right? So in this case, the utilization of all the resources in the storage layer is shared by all the namespaces, right? All the name nodes.
Well, in terms of utilizations, you can certainly overlay all those the multiple clusters on the same physical clusters, so they actually share the file systems.
But I think probably you're talking about some of the things that we were discussing in the past. But in that case, still a data node talks to only one name node, right? And if that name node is not making use of all the storage available in that data node, you cannot, now you have one cluster that's running out of space, another cluster that's relatively free. You cannot, share the storage that you have available in the storage layer, right, across all the namespaces.
OK, thank you.
Is there going to be a way to move something from one namespace to another?
So that's a good question, and this is again, why I qualify this as first phase. Right now, we don't have any, currently moving a part of the namespace from one name node to another name node involves copying, which means even though the storage is all, is being used, is being shared by the name nodes, you still need to make a physical copy. But we will look into, doing it as a namespace operation instead of storage layer operation. Right? So those are the things where we'll explore further.
Thanks.
Sure.
Over here.
Where is that? It's a surround sound. I cannot.
Hi.
Okay.
So in case of multiple namespaces, if you want to provide the high availability, wouldn't it blow up like the number of so earlier to provide high availability, you need like one node to basically replicate that. Now it is n times number of namespaces.
So what probably, right now what we are thinking is you'll have active and standby. And that's what the current thinking is. But we could probably explore different ways of doing that in the future and optimize the number of name nodes that you have.